Okay, in this module, I would like to discuss different optimization techniques that we use in the OR method. So it's the goal of this module to provide a review of basic optimization techniques using the fundamentals of calculus and numerical analysis techniques. So I'm sure that everyone watching this video has taken a calculus class at some point in their academic career, or at least hopefully they've been exposed to calculus and the ideas of calculus. And the field of calculus is ideally suited for optimization problems. The concept of the derivative allow optimization problems to be formulated and solved using established techniques. So just a little bit of an overview of what we're actually doing in calculus. Most of calculus is either differential calculus or integral calculus. So fundamentally, you're only really doing two things when you're dealing with calculus. Let's suppose that we have an XY coordinate system set up just like this, okay? And let's suppose that we have a function that looks like this. Okay, if you recall from your pre-calculus or calculus 1 days, something called the first derivative. If you remember what the first derivative does, essentially the first derivative tells you what the slope of the curve is at different points. So if you think about just having a straight line, let's suppose over here that we just have a straight line, okay? We can ask the question, what is the slope of this line? And it has an answer. Maybe the slope is equal to 1, maybe it's equal to 2, maybe it's equal to 1/2, whatever it may be. But the slope of this line is constant. It doesn't change. The slope at this point is the same as the slope at this point. It's the same at the slope of this point. Now, if we were to take and look at a curve like what I just drew here, and we were to ask the question, what is the slope of this curve? That question is almost nonsensical. This curve has no slope, okay? The best we can do is ask the question, what is the slope of this curve at any particular point? So I can say, what is the slope of this curve, the blue curve right here, okay? And I can go in and I can determine that. Numerically, it's pretty easy to do if you think about it. If we were to say zoom in on a part of this curve, say right here, okay? So let's zoom in and let's look at what the curve does. It kind of comes in, does something like that. Okay, and I say I want to know what the slope of the curve is at this particular point. Okay, if you didn't know anything at all about calculus, given enough time, you would probably be able to figure out how to get a pretty good answer. Okay, what you would do is you would simply just go a little bit forward, go a little bit backwards, probably by the same amount, and then you would just come in and draw a straight edge between those 2 points. And that would be a pretty good approximation for what the slope is of that curve at that particular point. And this is actually how the derivative, the proof of the equation that we use to find the derivative, this is how they actually do it. They just keep letting that interval get smaller and smaller and smaller and smaller. Okay? So we see this done all the time in calculus. And calculus, it's great for solving, I'm going to say, relatively simple, numerically continuous problems. When we get into discrete problems or functions that are pretty complicated, sometimes it's actually difficult to get these answers. Okay, so this is differential calculus. Integral calculus, which we're really not going to get into, but I just want to touch on, just because I said basically you only learn 2 things in a calculus class, is let's suppose that you have a curve that comes up and does something like this, all right? And you want to know, say, the volume of the curve from this point, not the volume, the area under the curve from this point to this point, okay? So what you do is you're just trying to calculate what this total area is, and you use something in calculus called an integral, okay? Now, we're not going to get into that. That's not really important in the context of this particular module, but that's all you're really doing in a calculus class. Yeah, you can make it more or less complicated, but for the most part, you're trying to figure out the derivative of a function or the integral of a function. Okay, so let's go back in. So let's take a look at a problem that you've probably solved when you were in high school if you were taking calculus or pre-calculus. Okay, so a man wants to build a rectangular enclosure for his herd of cattle. He only has $900 to spend on the fence and wants to enclose the largest grazing area for his money. He plans to build the pen along the river on his property so he does not have to put up a fence on that side. The side of the fence parallel to the river will cost $5 per meter to build, whereas the sides perpendicular to the river will cost $3 per meter. What dimension should he choose? Okay, so this is a classic calculus problem. So here's kind of a pictorial of what we're looking at. So we can see the side of the river. We're going to assume maybe there's a cliff or something there. The river's really deep and the cows won't try to swim out. So he only has to enclose 3 sides of the pen. So what should be the values of L and W such that he maximizes the grazing area while spending the least amount of money on fence? Okay, so let's go in and look at this. First of all, let's think about what the perimeter is, how much it's going to actually cost him. So the perimeter of the fence is L plus 2W. Okay, why is it L plus 2W? Well, because we have this length here, L, plus 2 times the length W. Now you may say, well, it looks like this W is a little longer than this W, but we're going to assume that they're the same length. But we do not have to add another L down here because it's bounded by a river. We could also have it bounded, say, by a large cliff or something that just goes into the side of a mountain. Okay, so the parallel side has a cost of 5 per meter, so this means that the cost of the side of the fence that is running parallel to the river is going to be 5L. So whatever the length of that fence is times 5 is how much that section of fence is going to cost you. The perpendicular sides to the river have cost $3 per meter, therefore the cost is 3 times 2W. So the total cost is then equal to 900. Okay? So we only have $900 to spend, so that means the total amount of money that we have to spend on fence is equal to 900. So that is where this equation right here comes from. Okay? Essentially, this side of the equation is the cost based on how much fence we're going to actually build, and this is the amount of money that we actually have. Okay? Now, let's look and see what the total area is. So the total area is equal to the length multiplied times the width. So if we put area, it's just simply going to be equal to length times width. Okay? However, from the previous expression, L can be written as a function of W. Now, how do we do this? Well, let's go in and say, can we solve for L right here? And the answer is yes. All we would do is simply subtract this 5L, and then we would divide out by, we would subtract. We would have 900 minus 6W, and then we would divide out by 5, and this would be equal to L. So we've simply found another way we can write L in terms of W. And this is important because we're trying to reduce this equation that has 2 variables down to an equation that has 1 variable. Okay? So I think that's pretty clear that L can be written as a function of W. Well, we know A then is equal to, we have W over here. So if we substitute this L here with this L here, then what we would have is simply 900 minus 6w over 5. Okay? And I've done that in this slide. So substituting the L into the original equation, we find 900 minus 6w over 5 times w is simply going to be equal to 900w minus 6w squared over 5. When you reduce it out, you get this equation here. Okay? So this is the equation that we are left with. Okay? Now, we want to take the first derivative of this equation. So how do we go about doing this? Well, before we do this, let's take a look. Okay, before we examine this and actually take the derivative of this equation, let's first take a look at what this graph might look like. So this is the graph we're wanting to examine. So we can see that this is a quadratic equation. So I'm going to bring this up in this software called GraphCalc. There's all kinds of graphing calculator software out there. But as you can see, this is the equation. It has this parabola shape, inverse. So we can see this has a maximum point. So I'm just going to zoom in on this. And if we just look at this and kind of eyeball it, we can see our cursor over here to the right, changing the XY positions. So I'm just going to come over here where I think it's about at the maximum value. And when I look at that, it says 74.70. I mean, if I move back and forth, I can't really tell, but it looks about to be about 75. Okay? Now, there's a tool that allows us to go in up here under 2D graph analysis and equation min and max. So I'm going to click on this, and I have to give it a lower bound and an upper bound. So I'm going to say, well, the lower bound, let's plug in 0 because right here we see at 0 it's not at the origin, it's not maximum. Over here we see this is 220, just a random number, the edge of the boundary, 221.3739. So I'm just going to plug in, say, 200, just a rough guess. Now I'll talk about what this does here in a few minutes, but let's just click solve and see what happens. And it says, sure enough, maximum found at 75, 6,750. Let me center the graph. So the computer used a technique to actually find that value. Okay, so let's see if we can do something similar using calculus. So if we go in and we take the first derivative of this function, 180w minus 6w squared over 5, here's what we find. Remember how to take the first derivative of just 180w? It's just going to be the constant, 180. The first derivative of 6w squared, we pull this 2 down, so 6w squared would equal to, fix that, is equal to 2 times 6 times w, and this is going to be 2 minus 1, or w raised to the first power. So that's where this 12w comes in. We leave this 5 here because it's a constant, and when we solve this, when we actually set this equal to 0, what we have is we would have 12w over 5 is equal to 180. Okay, so then we would have 12w is equal to what? 5 times 180 is 900. Is that right? Yeah, divide out by 12, and w is equal to 75. Okay? So that's where that 75 comes from. Also, now we can go in and we can plug in this 75 to our width out of our original perimeter equation and solve for L, and we get a value of 90. So what we find is that the width of the fence is 75 and the length is 90, and the total area is 6,750, which is the exact same value that came from when we actually solved this using GraphCalc. See, 6750. Okay. So that is how we would solve a very simple optimization problem using calculus. Okay. Now, optimization problems may be as simple or complex as the actual problem, the real-world problem requires. However, the previous problem has the property that the solution can be found in a closed form. So it means it has it has an exact solution. You can either write it as an integer, as a fraction. You could write it as a rational. So you may get something that looks like the square root of 2. Okay, that's still a closed form solution. Okay, so in this particular case, the problem has an exact solution of 50 and 90. Okay, so some problems require that the solution can only be an approximate. These problems have to be solved using a technique called numerical analysis. Now, what the computer actually did in GraphCalc just a moment ago is use numerical analysis techniques. Okay, there are courses, graduate level courses in numerical analysis. They can get very, very complex, especially when you're working with multidimensional problems. But the purpose of this module and the purpose of learning about this topic in this particular class is just to give you some basic exposure. I want you to understand what the computer is actually doing, regardless if you ever actually go in and program one of these or not. I want you to understand what the computer is doing. That way, if you ever plug in a problem and you can't get an answer, you understand maybe why, and that you have to change your initial starting conditions or things like that. Okay, often the function of interest is too complex to develop a simple closed form solution. In this case, special techniques using numerical analysis must be used. So numerical analysis is the study of algorithms for the problems of continuous mathematics. One of the most famous examples of this that is used probably more than any other numerical analysis technique, even to this day, was one of the first examples. And this is called Newton's method. It's also known as the Newton-Raphson method, named after Isaac Newton and Joseph Raphson. Is perhaps the best known method for finding successive better approximations to zeros or roots of a real value function. Okay. Newton's method can often converge remarkably quickly, especially if the iteration begins sufficiently near the desired root. Just how near sufficiently near needs to be, and just how quickly, remarkably quickly can be, depends on the problem. So it can be described as this. Okay, now, don't get excited about this. I know this looks a little complicated, but it's actually very simple. Before I get into the details, here's what I want to ask you. I want to pose this particular question. Let's suppose that you're given this problem, x squared is equal to 4. Okay? What is the value of x? Well, x is going to be equal to negative 2 and positive 2, right? So x is just going to be equal to the square root of 4, which has 2 roots. Okay, so let's suppose I give you a function like this: x squared plus 5x plus 6 is equal to 0. Okay, remember how to do this? This is simply going to be x plus 2 times x plus 3, and so we have 2 roots. X is equal to 2 and x is equal to 3, right? I'm sorry, negative 2 and negative 3. That's simple enough. All right, how about if I give you something like this? The logarithm of natural log of x is equal to 15. How do I solve this? Well, what you end up doing is you can raise each side to a power. You have to use the natural log, the e function. You can look it up in tables. So there's many well-established ways to actually solve this problem. So let's go in here, and if we put in something like, let's see if this will work, the natural log of x. probably need to zoom in on this. There we go. So this is what this function actually looks like. Okay. So you can see actually I have to go up rather high to get to 15. So let me plug this in. That was probably a bad example, but let's just go with it. Okay. So you can see actually right here is 15. So let's make this something like the natural log of x is equal to, say, 3. I think that's better. Okay. So how would we solve this? Well, the way we would solve it is we would go over here and we would take e raised to the natural log of x is equal to e, and let's make this 3, e cubed. So x is equal e to the third power, and this is simply going to be, see if I can bring up another calculator. So it's simply going to be 3, I don't even see an e on here. Usually most calculators have e raised to that power. So whatever the value is, let's just go in and solve it. That's the easiest way to do it. Intersections of two equations, solve natural log of x is equal to 3. So you can see that value is about 20. Okay, so 2.718, or e raised to the third power, gives you a value of about 20. Okay, so we can go in, and I'll just say this is approximately equal to 20. So we know how to solve problems like that. Simple enough. All right, let me ask you this question. Let's suppose that we go in and we look at something like this. X raised to the x power is equal to, let's say, 4. What is the value of x? Okay. Well, you look at this, you start trying numbers probably. 1, okay, 1 raised to the 1, 2 to the 2, okay, that's 2. So if I give you x to the x is equal to, say, 27, x is going to be equal to 3, right? What if I give you something like x to the x power is equal to 17? What's x equal to now? And the answer is, I don't know. And maybe you've never seen a function quite like this. But whatever the answer is, there's probably a very good chance that I'm not going to be able to write that in closed form. So I'm not going to be able to go in and write something like the x root of 17, even though that's the answer. But what does this equal to? It's not like I can write this is equal to the square root of 17 or the cube root of 17. These all are irrational numbers, but they're still in closed form. I can actually write them using standard mathematical representation and symbols. How do I write this number? And the answer is there actually is no easy way to do this. So we actually have to use a computer to go in and solve a problem like this. So what I'm going to do is I'm going to graph this function x raised to the x power, and I'm going to graph the function x equals 17. Okay? And I'm going to go in and see where these two cross. Okay? So let's go up here, 2D analysis, intersection of two equations. X to the x is equal to 17. My initial guess, a lot of times this is very important, and you're going to see why once we get into the details of how this process actually works. Guess of 1, I'm going to hit solve, and the answer is 2.775. And notice the y-intercept is almost equal to 17. Okay, very, very close. So if I were to come and use the calculator that I had just a moment ago, and I were to write, what was the answer? 2.7754 raised to the 2.7754. Look what I get. It's almost equal to 17. So probably to get it to be equal to 17 exactly, I have to take this out to an infinite number of decimal points. Okay. Well, I can't do that in reality, so what I do is I use the computer to iterate. So essentially what Newton's method is doing is it's just a sophisticated form of guessing. It's really not that much more sophisticated. In some ways it is, but not too much, of just trying a number, saying, that number was too small. Let me try a little bit bigger number. That number was too big. There's actually another method that we use. It's called the bisection method that actually uses that approach nearly exactly. So all I'm trying to get across with these examples is that sometimes you can't solve problems easily. You can't solve them in closed form. You have to use a computer. So this is what Newton's method does. And it uses this function here. And the idea of Newton's method is as follows. One starts with an initial guess, which is reasonably close to the true root. Then the function is approximated by its tangent line, and one computes the x-intercept of this tangent line. This intercept will typically be a better approximation to the function's root than the original guess, and the method can be iterated. So I'm sure that you've figured out what I'm saying with this definition, and now it's completely clear. Probably not. Let me give you an example of actually what's going on. Let's suppose that I have a graph that looks like this. Okay, and my graph comes down, and say I'm just interested in, okay, this part of the graph from here over. And I want to figure out where this x value is. All right, now we know the y value is going to be equal to 0. We want to figure out where this function f of x is equal to 0. So essentially we want to find the root. All right, so how do we go about doing this? It's actually pretty simple. Here's what we do. I want to extend this out just a little bit. I'm going to extend this down a little bit more, like this. Okay. We pick a point. So I'm going to pick a point, say right here. Okay. Let me see if I can get a straight edge to work. All right. Now what I do is I essentially bring a straight edge and I lay on this point, and I lay it parallel to the tangent of this point. Okay, so imagine if I drew a line and extended it on out. Okay, the tangent would look something like this. All right. So what I'm going to do is I'm going to take this blue function and I'm going to approximate it with this black line. Okay, this black line is just it's a simple equation, y equals mx plus b. Now, I can easily figure out where the roots of that line, where the root of that line, where it intercepts the y-axis. So I figure out where that point is. I come right here. I figure out where the point is, where the line, the black line itself, intercepts the y-axis. And then I take that x value and I plug it into my original equation. And it's going to come down about right here. So this is my error. This is how much I'm actually off. But you can see that this guess looks better than my original guess. Then I come in and I drop another tangent. A line that is tangent to the first derivative. Something like that. Would also kind of come down like this. Okay, and then I see where this new black line, okay, I see where the new black line crosses the origin, so I project up and right here. Okay, And you can see within 2 iterations, I'm very, 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 very close to where this original blue line crossed the y-axis. Okay? Now, it doesn't matter what this f of x is. You may say to yourself, well, why don't you just take the first derivative? Or why don't you just solve that equation? I'm sorry, just solve that equation and set it equal to 0. Well, that may be, like I said, something like x to the x, where you can't solve it. And so what you're doing is you're developing an approximation using Newton's method. Okay, so it's really pretty simple. Even though that big definition and the formula, it's actually very easy to go in and to derive that formula. Okay, so let's get started. So now let's take this function right here. F of x is equal to the natural log of x minus x squared plus 3. Okay. What I'd like for you to do right now is just pause the video and go in and see if you can solve that using what techniques you know about algebra. Just take a minute or two, go in and say, I'm going to solve this equation. Okay, I'm going to get the value of x, and then in a minute or two come back and you'll realize that there's no closed form solution of this. So a graphical analysis of the function indicates there are 2 real roots to this problem. The roots appear to be approximately x equals 0.05 and 1.9. And the way we know this is I simply went in and I graphed this equation. I just plugged it into GraphCalc or Mathematica or MATLAB or whatever graphing software you have, and you can see that there's appear to be 2 roots. One right here and one right here. Okay? Looks to be about 0.5 and 1.9. How do I know that? It's just kind of looking at it. Just kind of looking at the scale, 1.5, 1.6, 1.7, 1.8, about 1.9. This is 0.4, 0.3, 0.2, 0.1, about in the half, 0.05. And that's really all I did, okay? I just looked at it, okay? So what do? Well, the first thing we do is we pick a guess. Okay, we pick a number. So I'm going to plug in the number here about 1.2. 1.2. So I move up to this point right here. I drop a tangent line, and I see where this tangent line intersects the y-axis. Okay? And that looks to be about 2.1, 2.2, 2.3, okay? And so that would be my new guess. And then I would drop this tangent line down, and then I would move back up. Let's see if I do that, okay? So point C, I plug in as 1.2. This is just my guess. Where did the number 1.2 come from? I come up with it. I made it up. Why? Because it looked like it's going to be fairly close. Okay, and an important part of using numerical techniques is to come up with a good guess or a good estimate, and sometimes that can be difficult to do. So I plug in 1.2, and then I plug it into this formula. Okay, and you notice this formula was, when we go back, it's just the original function. Okay. Whatever the value, take the original function, plug in that value, take the first derivative of that function, plug in that value, divide these out, and then subtract that from your original guess. So it's really simple. Okay? So let's go in and take a look at it. First things first, 1.2. This is the easy one. This is my guess. So I plug in 1.2. Now I plug in 1.2 here. 1.2 and 1.2. And if you go in and you take the natural log of 1.2, subtract 1.2 squared, okay, and then add 3, what you'll find is you get a value of 1.74. So you may want to pause it and try that on the calculator just to see if you get a value of 1.74. Now, where does this function come from? This is simply the first derivative of your original function. So what is the first derivative of the natural log of x? It's simply 1 over x. What is the first derivative of x squared? It's simply 2x. What's the first derivative of 3? It's 0. Okay, so you're left with this 1 over x, so 1 over 1.2 minus 2x, or 2 times 1.2. Okay, and you should get negative 1.57. Then when you do all the math, you should get a value of 2.31, and that is this value right here. Okay, and then all you do is you simply repeat, starting over now with this being your new guess at point C. Okay, so let me see, I think I actually have this in the textbook that you'll be using. We go through and we actually solve this step by step. Yes, so you can see a value of 2.3. Then you just simply plug in 2.3 and you start over again. All right, and when you do that, you can see that it is approximately equal to where the graph crosses the y-axis. Okay. All right. Now let's suppose we wanted to find the leftmost root. Okay, which would be over here. We know it's a value of about 0.05. So I'm going to plug in a guess of say 0.1. And when I plug in a guess of 0.1, see how I get a value of about 0.0452, and then doing the next iteration, it gets closer and closer and closer. Okay, so let's go in now and see what the actual value of this equation is. All right, let's go up here under Zoom, go to Standard. All right, so here is my original equation. Okay, so here are my two roots. So what I'm going to do is I'm going to go 2D graph analysis. And I'm going to say axis intercepts, or I could set it equal to 0. And I want to let my initial guess start out at about 1.2 and hit solve and see about a value of 1.9. So it found this root, the root closest to this initial guess. If I plug in a value of say 0.1, see how it found the root over here, about 0.05. So now a question that one may ask is, which root will this find? Okay, does it find the root closest to the initial guess? And the answer to that question is that is very, very complicated. So like I was saying, that's a very, very complicated problem. It sounds on the surface like that should be a fairly simple problem, but this question was asked many years ago by a student who was taking a calculus or numerical analysis course. Asked the professor, what root does the initial starting guess iterate to? And the professor's first response was the closest root. And then that evening he went home and started actually experimenting with it. And here's an example of what he came up with. This is, I think, the function x to the 5th power. Yeah, x to the 5th power minus 1 is equal to 0. And each one of these colors represent a different root. So if you were to start, say, right here in this yellow color, this would iterate to this point right here. If you were to start in the purple color, it would iterate to this point here. But for instance, let's suppose you started right down here in this green color. This green would actually iterate over to this green color right here. So it turns out that that's a very, very complicated problem, and it's not trivial, and that was unknown until relatively few years ago. So that is how Newton's method works. Okay, and you can get as many decimals of precision that you need just by iterating. So Newton's method can be summarized as basically have an initial starting condition, determine the y value, take the slope, shoot a tangent line off, determine where that tangent line crosses the y-axis, and then start over again. Okay? It's extremely powerful, and in general the convergence is quadratic, meaning that the number of accurate digits is roughly doubled with each step. And this is just kind of a different practical considerations. Failure of the convergence of Newton's method can be observed for S-shaped functions if the initial guess is not sufficiently close to the root. Here's an example that you can see. So sometimes the problems with Newton's method is it doesn't always converge. Sometimes it diverges and heads off towards positive or negative infinity. So that's why I said it's important that you know what's going on. So if this happens, you can say, okay, let me change my initial guess, or let me try another root finding algorithm. So another root finding algorithm is the secant method, and we're not going to get into the details of exactly how it works, but it's very similar to the Newton's method, except the secant method uses 2 points instead of 1 point. So you actually have 2 guesses instead of 1 guess, and instead of drawing a tangent based on 1 point, you draw a secant based on 2 points, and you just iterate with using point 1 and 2, then you use point 2 and 3, 3 and 4, 5 and 6, until you get the level of precision that is desired. Okay, and this is the formula that you would use for that. Okay, there's a plethora of other root finding algorithms for both one and multi-dimensional problems. Some include the bisection method, false positive, Mueller's method, Brent's method, Haley's method, which was named after Edward Haley, the guy that discovered Halley's Comet, and Bailey's method. And later in the text we'll see how we can use some of these. Okay, so that basically wraps up this particular module. I just wanted you to understand how to use numerical root finding methods, and we'll see later on why they are important, because when we get into very complex problems, we're not going to be able to go in and solve these in closed form. We're going to have to use the computer. So read over the chapter, refer to any handouts, and be sure you complete any assigned homework.